Good morning. I'm happy to see you for the 8th semester. After we have dealt with cable-stayed bridges in their final stage during the 7th semester, we will now deal with their construction. Both are equally important. Of course, we need a proper and good design for the final bridge. But we must also, already during the design phase, have in mind how do we want to put the thing together. Both are equally important for bridge engineers, the general design and the construction planning and, of course, the construction engineering. Today we will deal with tower construction, briefly, that's not too much involved, and then of course with the construction of the beam, which shows a wide variety of methods for the three materials we deal with: concrete, steel, and composite. The cable installation in itself has a lot of varieties in it. Those construction methods for stay cables will be dealt with in a separate lecture later. In general, cable-stayed bridges have the advantage that their intermediate system during construction by free cantilevering, that their intermediate systems are stable compared to an arch bridge, which is stable only when the compression in the arch and the tension here work together. And so, before they are closed, we need to have some auxiliary supports, because the flow of forces during construction is not identical with the flow of forces in the final stage. The same is true for a self-anchored suspension bridge, which means a suspension bridge where the tension is in the hanger cable and this tension is taken up in compression in the beam. Self-anchored suspension bridge. There again, before the beam is not closed, we do not have this run of forces, which means we need auxiliary supports to build the beam. Contrary to that, a cable-stayed bridge, in the final stage, the load is carried up by the cables and back here, and the horizontal component is, as a compression force, carried in the beam. And the same is true for intermediate construction stage systems, where also we have the same flow of forces. The weight of the beam is taken up in the cable, it's balanced about the tower, and the compression force from the cable component is taken up in the beam. So intermediate systems are stable, and that is one of the big advantages of cable-stayed bridges, which has distinctly assisted their widespread use all over the world since the 1950s. It's always a question of economy. That's what we are talking. We are looking for the most economic type of bridge. And there, an important part of bridge cost is the cost of construction. For the same amount of material, one construction method is more expensive than the other one. So the total cost of the bridge will be different. As mentioned, we start with tower construction. First, steel towers. We use as an example the recent Strelasund Bridge, which connects the island of Rügen with Mecklenburg. And, I'm sorry, in this case, it was done the way that we have, I go back, we have here a steel tower on top of a concrete pier, and this steel tower was pre-assembled in pieces, and in this case the bottom part was connected to the first part of the beam, and this type part of structure was lifted in one piece up onto the concrete pier. We see it here installed, the beam is there, and we now go on piece by piece, lifting in with a floating crane the further steel tower pieces. We see here cross section. It's aerodynamically shaped. All the piers and tower of the Strelasund bridge are aerodynamically shaped for lesser wind load and for architectural reasons, I think. We see here a finite element view in the ultimate stage, and we see here the inner stiffening here is buckling. Anyway, we go up. We have here again the floating crane, which transports a piece of the tower up, and up we go. So we pre-assemble the pieces one after another and weld them together. Rather simple, straightforward. Concrete towers. We use as an example, the tower, the A tower of the Obere Argen Bridge in South Germany. And we see here, we build the tower legs generally cast in place. There are very few exceptions. Dee River Bridge in Wales or so, where we use precast elements. We do it cast in place. Then we have in free cantilevering upwards, we always have the possibility to use sliding forms, Gleitschalung, or jumping forms, Kletterschalung. Sliding forms may be a little bit more economic, but they have the problem that built-in items are sometimes not exactly where they should be because of the sliding process. So we as engineers should always prefer jumping forms, because there we have the time, also in adverse weather, to align the forms properly, to have the built-in items in place. Without being under time pressure, we must go on, we must go on, we must go on. So, free cantilevering preferably with jumping forms. In this particular case, an A tower, the two towers lean against one another, and after some time the bending moments in this construction stage from a cantilever as compared to the closed frame, these moments would be too big, would require additional material here, so we use temporary auxiliary struts in between the two tower legs, which take up the bending to the inside until we have a closed frame. The third material, as always, composite towers. Now, composite towers are composite only in the upper part of the cable anchorage. The bottom part is a regular concrete tower, but the cable anchorage is in steel. We see here a cross-section where we have a steel box, and inside the steel box, the stay cables are anchored. Looking at it in the longitudinal direction, we see inside here a steel frame which is cast into concrete at the outside. So the composite action takes place so that the vertical components from the cable forces run into the concrete from here down there. So we don't have to size the steel box at the bottom for the full vertical force, but it runs in here and the bending moments which take place here are also carried by the concrete. We used to call those concrete ears in that way that the anchor head is between the two concrete parts. We see here a detail of the cable anchorage. We have lock coil ropes in this particular case. We have here the steel box. We have openings where the cables run out, and they are supported here by webs, and cross girders take the horizontal the cable force into the outer steel webs. We see here a box lying ready for installation. It will, of course, in the final stage be vertical. What is here horizontal. These are the openings where the stay cables run out. And here we see shear studs, Schubdübel, which carry later the vertical component into these concrete ears, which will be cast otherwise. Here's a piece of steel lifted up to be placed on top of the concrete base and the steel anchorages. Now, after the steel anchorage parts are installed, a formwork has to be built up on the sides to cast these ears. And here we have a look. It's a little bit difficult to understand in the first moment. We look downwards. This is the steel part, and this is the outside where we have the shear studs protruding outwards, and there's reinforcement around in order to achieve the composite action. So, this is basically the way we build towers. Now we come to a more involved and different ways to build the beam. Again, we go by concrete beam, steel beam, and composite beam. The overriding construction method for cable-stayed bridges is free cantilevering. Sometimes for the approach bridges we have some others which we will show. So we start with free cantilevering, and then we always have in concrete the two possibilities: do it with precast elements or do it cast in place. So we start with free cantilevering by precast elements and show a few examples. Pesko-Kennewick bridge, which we will see in detail, I think, in lecture 25 or so. There are about, 32 precast elements. So it is proper to build steel forms. If we use the form only once, we build it, of course, from timber. But if we have many reuses, then it is effective to build a steel form. This is where the roadway slab goes, and that's where the webs go in. In this particular case, that was 1977, we used the short line casting method, which means we build only one element at a time instead of long line casting, where they're all cast in a long line. And in order to make the joints fit, joints are always a problem of the precast elements, to make them fit and how to connect them. In order to have a good fit here, we used what we call match casting, meaning the new element is cast against the end of the element before. So if we have a little deviation in here, that's exactly taken up by the new element. So they are match cast against one another, and they must fit. And so they did, actually. Now, after we cast an element, we then lift it, in this case with a portal frame, out of the forms, transport it to the water, put it on a barge, ship it by barge to the site, and then lift it up. We see here the lifting. In this particular case, we've used some hydraulic equipment on top of the beam to lift the beam elements. We will see other possibilities. In order not to overload the beam, we had to tie back this traveler to the tower. One disadvantage, of course, of precast elements is their heavy weight. This was about 270 tons, which is fairly typical, 300 tons for a precast element. And that, of course, is a very heavy load for the tip, so we need artificial tiebacks, which is a disadvantage also. Now, we wanted the two parts fit closely together. That's why we cast them one against the other. We glued them together, zusammenkleben, with epoxy resin, which was troweled on each side, like glue we use in the household. And then the new element is stressed with stress bars here, which run through here. And here we have a check. We stress them together so they harden under a certain minimum pressure until the epoxy is cured, is hard, and then we go on and lift the next one. Another example is the East Huntington Bridge. There the precast elements were cast long line, and here we see a typical cross-section. These indentions are for the shear transfer. They fit into one another, this corrugated part here, and can take up the shear. Because we have these heavy weights of, say, 300 tons, and if we free cantilever symmetric to the tower, we have overhang 300 tons with some 150 meter lever arm, and the tower may not be able to take that. So we have to stay the tower with auxiliary cables back here to the abutment and to the other end of the bridge. We build the tower, we have the starter piece on scaffolding, and then we start the free cantilevering with the elements transported again on water, lifted up until we reach here the approach joint, side span joint, close that with cast in place concrete. There we can't match cast when we come from the other side. We need a certain distance, so we use cast in place concrete. And then we go on free cantilevering in the center. We see it here in some pictures. The towers for the East Huntington Bridge are built, and we tie backwards and forwards the towers. It's of course an economic disadvantage. It costs money to have these auxiliary cables. And there's always a difficulty that a ship may run into this one. And it actually happened with the East Huntington. A ship ran into, thank God the cable didn't snap, and we were nearly done, but rather avoid them, I tell you. Here in this case for the East Huntington we used a floating crane. If you have one heavy enough for the 300 tons, good for you. You unload, or you do not have this heavy load on the beam. Makes construction easier. On the other hand, you have to rely on the water level in the river and all sorts of things. So there's always advantage for a derrick on deck against the floating crane one has to weigh, there's no general answer. Again, we go on with precast elements, a little bit different here. Example, we use the Posadas Encarnacion Bridge across the Paraná in Argentina. Basically the same system. We have an A-tower, we have precast elements, we have derricks on the deck, tied back to unload the beam to an auxiliary strut. We see it here from the front. But we had there a little trick, and that was after East Huntington, you know. So if you look at the tower, you see there's an auxiliary stay cable to keep the tower in place, but only backwards. Okay, you can do it this way. You either are here balanced, then this has a minimum strength, or you go one ahead only in the main span to stress this cable. And in that way you can get rid of the long, endangered by ship impact forestay auxiliary cable. Just by changing the method from one more here and one more there to either balance or only one more in the center span, and then you need only one backstay auxiliary cable. After the side span was closed, then of course the regular typical free cantilevering of the main span took place. All these bridges in Argentina, I think we did 5 of them, have in the range of 300 meters, 350 meter main span. Now, we've dealt with precast element. Advantage, the precast elements are built under controlled conditions, independent of weather and so on, and they can be done very precisely. And they have, say, 1 year or so of age when they are installed, so their shrinkage and creep capacity is greatly reduced against cast in place fresh concrete. Disadvantage is heavyweight, 300 tons for transportation and lifting. And how do you do the joints? Either match cast glued or cast in place joints. So those were precast. Now we come to cast in place. And we always have there, besides other things, the consideration: what happens to the cantilever moment which builds up from the tip over the length of the new element, the new length. The length of the precast, of the cast in place section, is the distance of the cables. So we have cable distances between 10, 12, 15 meters, and there we have then a free cantilever until the concrete is hardened and the cables are installed of something like 10, 15 meters. And then, okay, what's the beam depth? If the beam depth is only a tenth, 1 in 10, a cantilever is a very heavy moment for this shallow beam. If we have only, say, 6 meters and 4 meter beam depth, then we can do without. We will see examples. We start with slender beams and rather long cable distances. There we have an auxiliary cable to support the formwork traveler during construction. We see here, these are the final cables, and this is the cable which supports the traveler there. Looking on it from the tower head, we see here these temporary support cables supporting the tip of the form for the new piece of concrete anchored in the tower. Now this is quite a disadvantage, because you have to elongate these auxiliary cables for each new section, which just is time consuming. And in addition, you have to size these auxiliary cables for the biggest forces in the very last situation. So even for the very first element where we have steep cables and the force is low, we have to use cables so big that they can take up the 3 times bigger forces in for the final stage. So it's time consuming and costly. And the idea of reusing auxiliary cables normally doesn't work. This was the first step with auxiliary cables. Now we look into a completely different construction method, which I call auxiliary stays. We use an example, quite unusual example, the Flößer Bridge in Frankfurt. Now, this was done by architectural reasons, this design. So the engineers then had the task how to build it. We have, even in the final stage here, 50-meter distances. We couldn't place an auxiliary pier in the river. So how to build this thing? Well, you do it with auxiliary stays. We can have a certain free cantilevering, but then it's gone. Then the moments will be too big. So then we need an auxiliary cable to support each new section, which is expensive. But there is no other way when you do not have any supports here in the final stage. Here we see construction stage. We have here the many auxiliary stays. This is already the formwork for the single concrete backstay. In German we say Zügelgurtbrücke, you remember? We can't do that in English. We just say single, fore and backstays. And it's quite obvious when one looks onto here and says, I have all these nice stays, why not use them in the final state and make a cable-stayed bridge? That would have been more economic, but the architectural design was requesting just what we have seen, and that then caused this rather involved construction method. And so we must, that's why I say, when we design a bridge, not say primarily for architectural reasons, but for efficiency and economy, then we must have in mind, with the first start of a soft pencil on a foolscap size paper, when we make the very first design, how do I put it together? And when we think of single, fore and backstays, there must be some, I won't say alarm, but some consideration. Hey, how can I build it? And if we go not for architecture, but for economy, we very soon find we'd rather use a greater number of stays for ease of construction. Now, we then always tried to find a way to use the permanent stays in their permanent location, also already to support the erection traveler during construction. And with the Helgeland Bridge, we were the first time successful after a little thinking. So what we did is we said, okay, we use precast elements into which we anchor the permanent stay cables. So we have, before we even cast the beam, we have a permanent anchorage. And this precast element we tie with tie rods, bolts, onto the form traveler, which is underneath. So we place it in the form traveler, bolt it down, and install here the final cable in its final anchorage. It has not to be exchanged. Of course, we cannot use the final force. It must be rather longer. But we can use in this way, with precast element anchorage, the final stay already during construction. And we see it here. This is the already completed beam. This is the precast element with the steel pipe. The precast element is bolted down onto the formwork traveler, which we see here. And then, of course, we also have the horizontal component from the stay cable. We have to cater for that as well. So we had a precast strut, a precast beam from here touching the already erected beam. So the final cable was installed with low force, the vertical component taken by the bolts into the forms, the horizontal component taken by the strut into the already erected beam. And we were quite happy, except the handling of the precast element then wasn't so. Contractor was there, there must be a better way, but still, we liked it already. We see it here in detail. In erected beam, the form for the formwork, final cable bolted down here. This is a picture of this free cantilevering. We will see that bridge in greater detail at the end also, Helgeland Bridge. And here we look down from the tower, as we did already some time ago. But this, and we see here the prepared formwork for the next beam element. But in this case, these cables which support the carriage here, it's 12-meter distance, length of 12 meters. These are the final cables. So no elongation of the cables as with auxiliary cables. And restressing we need, but replacement and all that. So that is a fairly simple method. It took us some bridges to arrive at, but I think it's okay. Well, you can't beat not to use any auxiliary support, be it final, be it permanent. And that is only possible if we have a deep beam with short cable distances. That is the case for the second bridge across the Panama Canal. It was completed, I think, 2 or 3 years ago. We have here something like 350 meters. There's a beam with 4.5 meters deep. We didn't do this design. It was done by somebody else, and we did the detailed design and construction engineering for the contractor, Bilfinger. So we had to take this box, 4.5 meters deep, cable distance 6 meters. Now a cantilever, 1 in 6 to 4.5, 1.1 and 1.3, that works with a free cantilever, with a cantilever moment. We do not need any auxiliary support for that. This is the formwork, that's the direction of the beam. There were these U-shaped girders which run here on the deck. We see it here installed. And here we see it in action. This is the U-girder which grips around the beam and runs here on tracks. And this is the short form, again 4.5 meters deep for 6 meters. There the beam can carry that itself. So we don't need any auxiliary. We see here free cantilevering parallel to both sides. Again, because of the short lengths of elements, we had little weights left or right out of balance. So the moment about the tower was fairly small, and we didn't need any auxiliary staying of the tower. This was our troop, did it, my partner Rainer Saul and leading supervising engineer Karl Humpf, Stasile, and Enrique Hermann, an Argentine whose parents came from Germany, who spoke German, whom we had hired there, and they proudly present the completed bridge. Now, these were the classical methods of free cantilevering. Now we come to a few special methods which are rarely used. We start with launching. We're still in concrete beams. With launching of concrete beams, very often it's the approach bridges where we can use this type of construction. Kap Shui Mun Bridge in Hong Kong goes to the new Lantau Airport. And two half beams, this is one half in concrete, the side span built in concrete, main span built in steel. And we see here the concrete beam was built in parts here in the fabrication area, incrementally launched, next one built, and so on. We see here during construction, concrete beam. And as now in the final stage, we start here with the steel beam. We used the first sections of the steel beam as a launching nose for the incremental launching method, which sounds very reasonable, and it is. However, I warn, you need to make so many modifications to this first part. It's not simple, and it doesn't save you as much money as you were expecting. But we see here incremental launching of the approach concrete part with the steel, first part of the steel beam as launching nose. Now, another possibility is to build the bridge onshore and then rotate it across the water, which has been done for a few bridges. I use the example of the Ben Ahin Bridge. Contrary to your feeling, it's not in Arab, it is in Belgium, but it's called Ben Ahin Bridge across the Meuse River. A tower centered here, central anchorage tied back. And we see here the whole bridge was built parallel to the shore of the river on scaffolding. And then the tower legs here run together on a foundation, and we have sliding elements here and horizontal jacks which push it. Now, the sliding partners are normally Teflon, PTFE, polytetrafluorohexane, PTFE, and on the other hand, it's polished steel. That's what was found by Leonhard many, many years ago. Has about 4% friction. It's the same Teflon which is in your frying pan. It has the least friction factor with polished steel there is. And so there's a jack here and a jack here, and the jack strokes rotate the bridge by 70 degrees. We see it here until it is in final position, and then we lift the joint, cast it, grout it, take out the jacks before grout it, and then it's a regular final joint. Thank you. This was the first part of today.